Hello, sir.
Yeah.
Sir, shall we start, sir?
Yes, sir. We can start.
Sir, hello, sir.
Yeah. Yes, sir.
Okay, shall we start, sir?
Yes, sir. We can start.
Yes, sir. Okay, sir. Thank you, sir. Okay, so dear participants, very good afternoon to all. So welcome to afternoon session. Today, day 8, second session. So AICT sponsored 6 days online short-term training program on emerging trends and challenges in VLSI mixed signal processing. Person, Mr. Samuel Jigme Harrison to ST Microelectronics Asia Pacific Private Limited, Singapore. Welcoming, sir.
Thank you, sir, for the introduction.
Okay, sir. So before going to start the session, small introduction about today our resource person, introduced by Mr. Bhaskar.
Yes, sir. Very good afternoon to everyone gathered here. I hope that everyone had a lunch and being ready for the session. Education is not a filling of a pail, it is a lighting of a fire. In this way, I'd like to give a short intro about our resource person, Mr. Samuel Jigme Harrison. Samuel Jigme Harrison started his engineering education from St. Joseph College of Engineering, Chennai, with a bachelor's degree in the field of electronics and communication engineering at 2008. He then completed his master in science specialization on integrated circuit design, a joint degree from a Nanyang Technological University, Singapore, and Technical University of Munich, Germany at 2010. He also holds a master's in business administration from Anglia Ruskin University, UK. During his studies in these three institutions, Samuel published journals and papers in different conferences and national level symposiums. Samuel started his career with the Avago Technologies, Singapore in 2010 as an entry-level IC design engineer. He then got promoted as a senior ASIC design engineer in 2014 and the company was renamed as a Broadcom Limited Singapore in 2016. Samuel is currently working with the ST Microelectronics Asia Pacific Private Limited, Singapore since 2017 as a senior digital IC design engineer. He has more than 10 years of experiences in a VLSI, specialization in a physical design implementation with 90 nanometer, 65 nanometer, 40 nanometer, 60 nanometer, and 7 nanometer technologies, and coverage areas like floor planning, place and route, clock tree synthesis, static timing analysis, and physical verification. Samuel received a Technical Merit Award in a SNUG Penang at 2018, conducted by a synopsis for presenting a paper titled A Novel Approval in a Security Implementation and Clock Tree Synthesis Using a ICC2. He has also published an article titled Importance of Security in IC Design by the Singapore Semiconductor Industry Association in the technical magazine Singapore Semiconductor Voice in May 2019. He is a fellow member in the Indian Society for a Very Large Scale Integration Education, Ranchi. He is also membership in technical bodies like VLSI Society of India, Semiconductor Society of India, IEEE and IEEE Solid State Circuit Society, IEEE Computer Society Technical Committee on VLSI, Internet of Things Community, IEEE, and so on. In this way, now I like to hand over the session to our resource person, Mr. Samuel Jigme Harrison, who is going to handle the session on the topic of physical design and its role in the semiconductor industry. Please, sir.
Thank you, sir, for the brief introduction. And once again, I sincerely thank the institution for giving me this opportunity to be a resource person in today's webinar. And I also welcome all the participants, faculty members, research scholars for this session. And I hope that this session on physical design and its role in the semiconductor industry will be useful for each one of us today. So I will share my screen now.
Yes, sir.
Okay, so moving on to today's presentation, I would like to give you some insight about the semiconductor industry in Singapore. The first semiconductor organization was opened in 1968, and Singapore houses more than 60 semiconductor companies with around 35,000 employees. And this is one of the largest industry in Singapore, which contributes to the country's economy and is 7%. So we have the major design houses of all the semiconductor companies, and even some companies, they consider Singapore as their Asia Pacific headquarters. Okay, so my workplace is ST Microelectronics, which is Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its corporate headquarters at Geneva. So we serve around 100K customers and with 11 manufacturing sites all over the globe. And there are a total of 46,000 employees worldwide with 18,000 active patents. So for today's presentation, I would like to focus more on physical design, which is part of the digital IC design flow, where physical design is a process which transforms a digital circuit into a physical layout. So we all know that in the IC design flow of digital design, we have a front-end and back-end design. And in front-end design, we have VHDL Verilog codings being written, and we have a schematic digital representation. Whereas in physical design, this schematic digital representation is converted to metal layers. And the function still remains the same. Only thing, the circuit is being transformed into metal layers. And after backend design, or just the physical design, the output is given to the manufacturing foundry. So the manufacturing foundry requires their input in the form of metal layers. Connections between A to B in the netlist in the front-end design will be connected in the form of metal layer between input A and the output B. So this is how the transformation happens. So here you can see the IC design flow, where you have system specification, which is the customer's input and their request, and architectural team takes in the request and they do the architecture for the chip. And the functional design and logic design is done by the front end team. They include Boolean logic, NAND gate, NOR gate, etc. And their output in the form of circuit design is given to the physical design team. So physical design team takes it, and partitioning, floor planning, placement, clock tree synthesis, signal routing, timing closure happens in this step. So after physical design, physical verification occurs, which is DRC, LVS, ERC. All the physical checks are being done. And once the physical checks are being done and it is clean, then fabrication happens. So fabrication is where the physical design output is given as input to fabrication plant, and the chip is being manufactured there. So after that is packaging and testing. And after packaging and testing, the chip looks like this, with all the casing in black color and all the metal pins on both the sides of the external pins on both the sides of the chip. So this external pins, when placed on a digital circuit board, will be connected to the other components in the board. So this is the IC design flow implemented for manufacturing a chip. So what are the inputs to physical design? The inputs to physical design are a netlist, which is the VHDL Verilog coding, and library information of the cells in the design. So library information is nothing but all the design will include standard cells. So, and each standard cell will have library information where the timing information is given for all the cells. And a technology file is also given as input with the manufacturing constraints. So the technology file is technology specific, like a 40 nanometer technology file is separate, and then it's the timing constraints. So all these are the inputs to physical design flow, and the timing, power, and design constraints are to be met. So All these are the important criteria to be met in physical design, which is timing, power, and design constraints. What are the steps in physical design? The main steps in physical design are floor planning, power planning, placement, clock tree synthesis, routing, static timing analysis, and physical verification. So we will go through these steps in brief in today's presentation. So first is floor planning. And floor planning is the critical and foremost step in physical design. So it is same as how an civil engineer comes up with a floor plan to build a house or a project. So it is like he has to decide where to place the hall, where to place the entrance, where to place the gate, and so on. So all this comes with experience and his exposure to many projects. The same thing happens in IC design flow, where the floor plan is being done by the physical design engineers. The floor plan has to decide the size of the floor plan and where to place the macros and where to place the pins, etc. So this actually comes by experience. And what are the goals of a good floor plan? Goals of a good floor plan are minimize total chip area, routability of the design, minimal congestion, low power consumption. So when there is less congestion, then there is low power consumption in the design. So all these are goals of a good floor plan. So what are the steps in floor planning? The first step is to determine the size of the chip. And the second one is IO pin placement, macro placement, creating standard cell rows, adding routing and placement blockages. So all these are steps in floor plan. Okay, so floor planning can be controlled by two parameters. One is aspect ratio and one is core utilization. So in aspect ratio, it is actually the width to height ratio of the chip. So width can be related to horizontal routing resources and height can be related to vertical routing resources. So this is actually the aspect ratio, and it is actually number of horizontal routing resources by number of vertical routing resources. If your aspect ratio is 1, then the block shape will be a square. And if your aspect ratio is greater than 1, then the block shape will be rectangle with more routing resources in the vertical direction. So your height is greater than your width. And if your aspect ratio is less than 1, then the block shape will be a rectangle with more routing resources in the horizontal direction. So your width is greater than your height. So all these are like different aspect ratios, and majority of the projects, they have aspect ratio greater than 1, so that you have more routing resources in the vertical direction. Okay, the next step is core utilization. So we need to calculate the area occupied by standard cells and macros in the design. So how do we come up with this core utilization? It is actually the standard cell area plus macro area by the total core area. So for example, we are aware of the macros to be placed in the standard cell in the chip. So we need to calculate the x and y of each macro, and then we are able to calculate the area of the macros, and then the left out portion is the area for the standard cell. So we calculate that area and we sum it up for this core utilization calculation. So if your core utilization is 0.6, it means that 60% of the chip is already being used for cell placement, and you have left with only 40% for signal routing. So if in case your chip utilization is 0.7, then we have a hard time in routing because we only have 30% for routing resources. So we need to make sure that we always have a core utilization between 0.5 to 0.6. So your routability is feasible and it can go through. Okay, so the next one is in each floor plan, we have core rows in the center of the chip. So the core rows play a major role where the standard cells are being placed. So the height of the core row depends on the height of the standard cell. So core rows are nothing but the places where the standard cell is being placed. So what happens is like alternate core rows are always flipped. For example, you have a standard cell which has VDD at the top and ground at the bottom. So you place it on a core row, and the next core row, the adjacent core row, if you again place the standard cell without flipping the core row, what happens is the VDD of the second core row at the top will short with the ground at the bottom of the first core row. I'm sure that you are able to visualize it, like when you place two rows, one on top and one at the bottom, two cells, one at the top and one at the bottom. If they are not flipped, the VDD of the second cell will short with the ground of the first cell. So in order to avoid it, all the alternate rows are flipped so that the ground of the second cell will overlap with ground of the first cell. This will not create any shorts, and so this is why all the core rows, the adjacent rows are flipped. Okay, so next is spacing between macros. So we might have seen in floor plans where a minimum spacing must exist between macros for pin shades. So for example, you have channel spacing where number of pins into pitch by available layers by total layers. So the pitch should correspond to the topmost metal layer among the two macros. Now open spaces also should be avoided to the minimum. Macro placement. The pin of the macro should always face towards the logic area, which is the center portion of the chip. So we need to make sure that we don't place the macros in a way that the pins are facing the outward region. So pins are always supposed to face the internal region. And we use a data flow diagram. So data flow diagram is provided to you by the customer. So data flow diagram will have the full detail of the floor plan, like which macro communicates with which macro, which standard cells are communicating with which macro, etc. And we need to make sure that the routing channels between macros is big enough to accommodate the signal routes and power strips. Macros can also be abutted with the pin sides in the opposite direction. Okay, the next step is adding blockages. In a floor plan step, there are two types of blockages to be added. One is the placement blockage and one is the routing blockage. So when you add placement blockage, what happens is all the thin spaces, small empty spaces around the chip should be covered by placement blockage. The reason is, like when we allow the tool for placement, if there is some small opening, the tool will try to place the standard cells in those openings. So which will cause later congestion in the design. So what we have to do is we need to make sure that all the empty spaces around the chip are covered properly with placement blockages so that you have complete area in the center and the chip can place all the cells in the center. The next one is the routing blockage. Actually, this routing blockage prevents routing of metal layers in the blocked region. This is actually required when you try to do full chip routing on the full floor plan and you have few macros which already have metal 4 routes. So the metal 4 routes of the floor macro shorts with the metal 4 route of the full floor plan. So what can be done is you put a metal 4 routing blockage on the macro so that the tool will not route over the macro, so which will prevent the short. Okay, so this is actually an interactive session of the design layout, and it is from the tool called Inverter. So Inverter is a tool from Cadence. So there are two tools which can be used for physical design, which is Inverter and ICC2. ICC2 is from Synopsys and Inverter is from Cadence. Majority of the companies, design houses, they use Inverter from Cadence. So this is actually the GUI, and at top you have the menu bar, and at the bottom you have the toolbar, and at the top you have the directory name. So when you open a database, you will be able to see the directory name at the top. So it will make sure, it will help you to ensure that you have opened the right database, because this is a very complicated and very challenging work. So we need to make sure that no mistake happens, because it's like millions of dollars are involved in each project. So we need to make sure that we open the right database, we do the fix on the right database is analyzed, and so on. Okay, so and then we have design views, various design views for you to debug, and also online help portal is here, and you have a layer control bar where we have standard cells, physical cells, and then you have blockages. Then you have congestion, and you can select the congestion maps here. So after each run, you can open the design and you can check the congestion. And then you have the various types of layers. So you can enable, disable these layers for debug purpose. And here, if you see, you have a coordinates area. So if you keep your cursor in any of these locations, this number will change. And then you have a query here. And then if you click a net, the net name will be displayed here. So all these are like some information for you in the interactive session. Okay, so this is how a routed design will look like, where you have pins at the boundary of the chip, and all the pins are properly connected using metal layers. And around the macro, you have VDD and ground. So VDD ground power stripe and VDD power stripe is drawn here. So it is mandatory that around each memory and each IP, we have to draw this VDD and ground power ring. So this power ring is a part of power planning, and I will explain to you in the later slides like how to do this step. Okay, so this is actually an example for macro placement, where you can see that there are groups of macros in light blue, dark blue, and orange, and so on. So it means that all these macros are of the same color and they communicate with each other. So we are able to place it close to each other in order to avoid any routing or any buffering. So if there are long routes in between, the tool during optimization might try to add buffers. So all this is avoided in this process. So when you place the macros neatly and around the boundary of the chip, you can see that in the center you have a good amount of space for the standard cell placement. Okay, so that was floor planning, and this is the next step, which is power planning. Okay, so what are the goals of power planning? We need to make sure that proper power mesh is being created with VDD and ground, which means that all the VDD and ground pins in the design, it may be of a macro or a standard cell or any part of the design, all the VDD and ground pins should be properly connected. So and also the main goal of power planning is to meet the IR drop budget. Okay, next is the power plant components. First one is block ring, core ring, routing standard cell pins, adding VDD and ground stripes in the core area, and we connect the pad pins, we connect the block pins. So block ring is what I mentioned earlier, like around each memory or IP, we have to draw block rings, which is VDD and ground block ring. And then the core ring is around the boundary of the chip, and routing standard cell pins. So all the standard cells will have power pins. So all these power pins should be connected, and it should be connected to the main power grid. And also we need to add VDD and ground power stripes in the core area. So all this I will show you in the later slides with some images. Okay, so what are power pads? These power pads actually are very important to the chip, as they supply power to the chip the power is connected to the vertical and horizontal metal stripe. So the next one is block power rings. These are power stripes around the macros, and the width of the power stripe and spacing between the power stripes are calculated by the designer. The third one is horizontal and vertical power stripes. So VDD and ground power stripes are drawn over the entire section of the die. So the horizontal wire is known as stripe and the vertical wire is known as trunk. So block rings, the standard cell power rails, all are connected to the main power pads through VDD and ground. So actually the power stripes, they have to use the highest metal layer and the widest metal layer. For example, you have 6 metal layers in the design. The 6th metal layer will be thick and which is the highest routing layer, is used as the power stripe layer. So the main reason is, since the metal layer is thick, there is more flow of current and less resistance. Okay, the next one is a standard cell rail. So this is nothing but actually the standard cells placed on the core rows. They are actually being connected to power grid. So how do they do it? They can be connected using a structure known as follow pin, which is in either M1 or M2. So these follow pins are the main source of contact for power in standard cell rails. And as I mentioned earlier, the row orientation of the alternate standard cells rows is flipped. And the IO pad placement. So we need to make sure that sufficient number of VDD and ground pads are present on either side of the chip for uniform power distribution. And power dissipation and IR drop also should be taken care into account. So the main idea of power planning is to make sure that there is proper connectivity from ground and VDD pads to the entire area of the design. So this is actually the main aim of power planning. Okay, now if you see here, you're able to see the snapshot where you have core rings at the boundary, which is VDD VSS, and you have pads, power pads, which is VDD here. You can see that the blue line is connected to VDD, and this one is connected to VSS, which is ground. So you have pads, and you have the horizontal one is known as trunk, whereas the vertical one is known as straps. So the main concept here is, if you see here, you can see that there are yellow lines flowing through. These are actually the standard cell rows, and you can see that the standard cells are placed here, and they are properly connected to power using the follow pins. So this is how basic power planning output will look like. Okay, here this is actually an interactive session where you have a macro in between and surrounded by VDD and ground power stripe. So this is known as the block ring. So you have VDD block ring and also ground block ring. So this actually can be drawn using a script in the Innova's window, or also you can you at the top you have few buttons so that you can go through the procedure, and you can also draw this block power ring. So it is a must for all the physical design engineers to take care of this power planning structure. Okay, now if you see here, after the core rows is connected to M1 follow pin, and you can see that the blue line is the M1 connection. So the core rows are connected to M1, and here if you see at top it is connected to ground, at bottom it is connected to VDD. So at the top the connection stops with the ground. Okay, so this is properly connected database, and here also you see that the main power stripes will go through the block, which is ground and VDD. So this is how power planning is being done. The third step is placement. And what are the objectives of a good placement? The main objectives of a good placement are timing and power. So we need to make sure that the good placement can contribute to closure of timing, which is setup and hold time, and also power consumption is less. And also you have a routable design, and you have good control over congestion, and you have minimum timing DRCs. Okay, there are 3 steps in placement, which is global placement, legalization, and detailed placement. So, but all this happen internal to the tool, and you won't be able to see it outside. But a placement step will generate a log file. So this log file will have all the information of the inputs, outputs, what was the requirement, and what can be achieved, and so on. So global placement actually is where the tool finds an approximate location to place all the cells. So in global placement, what happens is the tool just dumps in all the standard cells, and the cells which are placed are opposite, overlapping with each other, and they do not align with the power rail. This placement technique actually is quite fast and accurate for initial timing and congestion analysis. So this is actually global placement, where the tool just dumps in all the standard cells in the design. Here you are able to see how is global placement being done. Here if you see, there are macros, and at the top you have standard cell rows and standard cells. And you can see that the standard cells here are not placed on the core grid. It is actually overlapping with each other, and is also randomly placed. So this is a result of global placement. Next is legalization. Legalization is where the tool moves the cells to the proper location so that the cells are properly aligned to the routing tracks. So this is actually the main step in placement, where legalization, it ensures that the cells are neatly placed, and they are actually capable of getting the power. The next step is detailed placement, which also contributes to 50% of the runtime. It is actually the step where minor modifications happen in the floor plan. So because in legalization, almost all the cells are being moved properly to cater to timing and congestion, but there may be some places where the legalization cannot occur. So the next step is detailed placement, where the places where legalization cannot occur will be taken into account and modified accordingly. Okay, there is this step called placement bounds. So what is a placement bound? Actually, a placement bound is nothing but a group which actually contains a number of standard cells, and these standard cells communicate with one group, or actually they communicate with one particular macro. So what happens is, in the case when we don't have this placement bound, the tool will, during placement, it will place the standard cells quite far away from each other, even though they belong to one group. So this will actually result in more timing issues, because the reason is the routes are longer, and you need to add buffers, etc. It will either fail hold time or setup time. So what happens here is this constraint actually controls the placement of the group of cells, and this procedure is followed to minimize the wire length. So this actually happens only in critical designs, and we can have this as a standby option to clean up timing. Okay, the next step is addition of spare cells. In placement step, we are forced to add spare cells without fail. So what is the use of a spare cell? For example, if we have Apple iPhone 10 with us, and the company decides to launch Apple iPhone 12. So we still have the working directory of the iPhone 10 with us. Working directory is the output of physical design. So what happens is the customer after 2 years, he comes up with a plan to put up iPhone 12. And he gets back to you because he's more convinced with your work, and he gets back to you and says that we need to incorporate a few changes and release the new iPhone. So in order to use the new corrections, what we need to have is we need to have spare cells in the design. Only if you have spare cells in the design, you will be able to do these new changes which has come to you after 2 years. So if you don't have this facility, if you don't have any spare cell, then the tool will not be able to accommodate any ECU changes in the near future. So we need to make sure that we have spare cells. These spare cells are just dummy cells and they don't have any function in the design. So when you have the version 2 of either iPhone or some other product, you can just incorporate the changes accordingly. So this is actually difference between good placement and bad placement. In good placement, you see that the cells are neatly placed and the pins are actually surrounding the chip, and also you have proper fly lines. Whereas in bad placement, it doesn't occur, where you have all the pins clustered to one region, and you have the fly lines going all over the place. Okay, so what is the difference between good placement and bad placement? Decrease in area and length of wires leads to good placement. Increase in area and length of wires leads to bad placement. Easier routability is a result of good placement, and difficult situation of routing is bad placement. So in good placement, you have shorter wires. These shorter wires contribute to less power consumption, whereas in bad placement, you have long wires and they contribute to high power dissipation. So there are less hotspots in good placement. The hotspots in the sense there are less areas which needs rectification. And for bad placement, we have more hotspots in the design, and we need more time to fix these issues. So these hotspots actually are results like bad congestion, bad timing issues, and so on. Okay, so congestion is a very major topic to be dealt with in placement and other steps of physical design flow. It occurs if the number of available routing resources is less than the required routing resources. A congestion map can help us to visualize the quality of placement. So after each step, you can open up the design and the interactive session. You can click for congestion, the plus symbol, and a drop down menu will be there, and you can select the congestion map to analyze the issue. Okay, what are the reasons for congestion? High standard cell density create hotspots, no proper placement blockages, less routing resources, placement of macros in center of the chip, and tool does buffering during optimization. So all this contributes to congestion. Okay, what are the strategies to fix congestion? We can identify areas with low utilization and modify the floor plan accordingly. Spread out the top level ports or move to other sites. So you can control the placement of this top level ports, and then you can run a quick placement to check the congestion. And you can think of increasing the spacing between memories, macros. You can add proper blockages and halos, and also you can do block resizing to reduce the overall congestion. And macro pins should always face towards the logic region, which is the core area of the chip. So now if you see here, we have completed placement, and all the cells are placed in the design in the center. But you can see that there are few empty spaces in this chip. So later I will explain to you in during route step on how to fill these empty spaces. So this is actually a step-by-step procedure for you. Once you complete floor plan, you complete power planning, and then you do your next step, which is placement. Okay, so at the end of placement step, you will look at a design like this, which has all the trials trial connections. So this is actually not routing, but it is actually a pre-route kind of structure which you are able to see during your placement step. Okay, the fourth step is clock tree synthesis. So we are left with clock tree synthesis, routing, static timing analysis, and physical verification. So clock tree analysis. Okay, so I'm not sure about your knowledge for clock tree synthesis. So let us go through some basic information on clock tree synthesis. Like you have a clock source, and this clock source actually communicates with all the flops in the design. So if you are able to see, the distance between these two is short, whereas the distance between this flip-flop and this clock source is quite long. So the tool finds it very hard to balance this. So what happens is we add clock buffers and inverters in the design. So when you add clock buffers and inverters in this path, even though the path is long, the tool will try to align these two paths together based on the delay. So this actually will help you for the chip to be balanced properly, and we will be able to fix timing, hold time and setup time easily. Okay, so before moving on to clock tree synthesis, I just want to highlight to you that for placement step, we need to make sure that density is 50 to 60%, congestion is less than 1%, both horizontal and vertical, and also the clocks are not propagated in placement step. So it is only we check for setup time in placement step, and for the subsequent steps we are able to check both setup time and hold time, because all the clocks are propagating in the second phase. So what are the objectives of clock tree synthesis? We have to minimize skew, we have to minimize the insertion delay, and the maximum transition and maximum capacitance. So what are the effects of clock tree synthesis? The effects of clock tree synthesis are, it includes addition of clock buffers and inverters. So once the CTS is performed, we have addition of clock buffers and clock inverters in the design. These clock buffers and inverters are quite big in size, and they contribute to more power consumption. So we need to make sure that less number of clock buffers and inverters are added in the design. So when you have more number of clock buffers and inverters, it will lead to congestion. Next is how is CTS achieved in the design. We have addition of clock buffers and clock inverters to minimize the skew, and we have to balance the clocks, and the non-default rules are being used also to the clock nets. So I will explain to you the non-default routes in detail in the later slides. So now, what is clock buffer and what is clock inverter? Clock inverters are used for clock tree building, whereas clock buffers are used for clock tree balancing. Clock buffers have equal rise and fall time because the normal buffers have unequal rise and fall time. So that is the main reason for clock tree synthesis we are able to use clock buffers. And clock buffers actually are increased in size than the normal buffers. Okay, here you are able to see this image where there is a launch clock and where there is a capture clock. So the launch clock actually connects to a register, a flip-flop, and there is combination logic in between, and there is a capture clock. This capture clock actually is a delay included by the combination logic. So you have launch clock and you have capture clock. The delay is nothing but the skew. So how can this delay be reduced? If we fix the violations in combination logic, if we reduce the combination logic, length of the combination logic, then in that case we are able to meet the skew. Okay, there is min delay and max delay. You have a launch clock, you have a timing capture clock. So the min delay is nothing but the start to the before the active edge, where it is the min delay, and for max delay it is actually calculated as 1 clock cycle. Okay, so a few definitions of clock tree synthesis. We have skew, where it is the difference in clock arrival time between two different registers. Here is an example for pre-clock and post-clock representation. So before clock tree synthesis, you have a clock source and it communicates directly with all the 4 registers, whereas now you have clock buffers in between, so they are able to balance the distance. So we put clock buffers in between and we build up the clock tree. Okay, so previously those days we are working on a clock mesh. Clock mesh is nothing but you just draw a complete mesh over the chip. So complete mesh of VDD and ground. And what happens is, even though if there are no flip-flops or registers in a particular region, this clock mesh will still function. So this actually will contribute to a lot of power consumption and a lot of problems with the timing closure. So what we now suggest for companies, and companies make use of, is clock tree synthesis, where buffers are inserted based only on the requirement. When there is a need for optimization, or when there is a need for clock tree synthesis, in that case the clock tree is being performed. Okay, so how do you achieve a proper clock tree? We need to pre-route the clock nets, and we need to use higher metal layers, and clock nets should be shielded. So clock net should be shielded in the sense there should be a clock net in middle, and it should be surrounded by VDD ground, VDD ground. So this will actually ensure that the clock net is shielded. Okay, non-default routing rules. Actually, these rules consist of double width, double wide, or triple spacing, triple wide with double wide spacing, etc. These rules actually are used to route only clock nets, and they do not touch the functional nets. And one more thing to notice, before moving on to clock tree synthesis, we have already completed the first route, which is the power routes. So during power planning step, all the VDD and ground nets are already routed. So the second chance for routing is only for clock nets. So clock nets also use higher metal layers, and they actually have more room for routing, because during clock tree synthesis the signal routes are not signal nets are not routed yet, so it gives more room for the next step. Okay, so this is actually a GUI, an interactive session which is opened up after completing the clock tree synthesis step. So here you can see there is a clock tree structure, and there are flip-flops, and there are flip-flops, and also there are clock buffers and inverters being added. So each clock buffer and inverter, if you click these inverter buffers, you'll be able to know the details of the inverter buffer, and at bottom you have your skew group, skew, min delay, max delay, etc. So this actually is known as CC-opt debugger, where you are able to visualize your chip in the form of clock tree synthesis. Okay, next step is routing. Okay, routing is a more challenging step, and the goals of routing are to minimize the total wire length, minimize the critical path delay, minimize congestion hotspots, minimize the number of metal layer changes. So all the goals of placement, floor plan, routing, everything is more or less the same. The ultimate aim is to have less congestion in the design and make the design routable and so on. Okay, as I mentioned earlier, we have a routing order where power routes are being routed first, next followed by clock routes and then signal routes. We have already completed power routes, VDD and ground has been routed. We have already completed clock routes in the previous step where all the clocks are being routed. The next one is signal route. So in route step, all the signals are being routed. Signals are nothing but the signal nets, and they actually perform the main function in the chip. So all these nets are then routed. So the entire routing resources can be used at this stage as power and clock nets have already been routed. Okay, routing grids. So the routing grids actually are defined for the entire layout, and the routing direction is defined for each metal layer. So for example, M1 will be assigned horizontal routing track, whereas M2 will be assigned a vertical routing track. So it goes on like this, and alternate metal routing tracks are superimposed with each other. Here you are able to see a pictorial representation where there is vertical routing track and where there is horizontal routing track. Okay, I hope that you're able to see this image where you have metal 1 in horizontal direction and metal 2 in vertical direction. So metal 1 is starting from a standard cell, and you have a metal 1 structure. This metal 1 structure is then moved to metal 1. This metal 2, sorry, is moved to metal 1. And when you move metal 2 to metal 1, a via should drop in. So we need to make sure that we have a via, which is an interconnect between metal 2 and metal 1. So this via is must, and only if there is a via, even though it's a change from metal 2 to metal 1, without via, this change won't be accepted. So each and every part of this physical design job is quite critical and very challenging. So we need to make sure that we do the good job and we put full efforts in fixing, timing, and cleaning the chip. Okay, so what are the stages of routing? So as in placement, we also have 3 stages of routing. So in placement, we had detailed routing, global routing, and detailed routing. So here you have global routing and also detailed routing. So global routing is followed by track assignment. Okay, so this is an example of global routing where you see that routes are not being confirmed. It is only traces of routes. So this actually is detailed global routing. So it is same as global placement where the cell just puts in the values and they are not cleaned. So same happens in global routing where the traces are being put up, and from there it gets optimized in each step. Okay, so what are the objectives of a good global floor plan, global routing? So we minimize overflow of congestion, reduce total wire length, runtime reduction. Actually, routing is of two kinds. One is time-driven routing and one is crosstalk-driven routing. Time-driven routing is like the wire delays are calculated before global routing, and I will explain to you in the next few slides like what is crosstalk and how it can be avoided. So there are two types of global routing. Tool takes care to make sure that timing is met and also we don't have crosstalk. So this is actually tracking assignment. It is same as legalization in placement, where the routing resources are channels are allocated and the routes are already predefined in this step. So after tracking placement, it is almost complete and neat. So this is actually detailed routing. In detailed routing, you're able to see that all the routes are neatly drawn. Okay, so after routing, when you click on the congestion map, this is how it looks like, where you have blue color spots all over the chip. So here, what happens is there are no congestion, and in between there is a region which is red in color, which is a hotspot. So as a physical design engineer, we need to understand the violation, we need to debug, we need to go into the design and look and find out why this region is showing hotspot. Maybe in that particular area or the nearby areas, there may be no proper connectivity of VDD and ground. So this actually will also lead to congestion, and also maybe the macros are too close to each other, or the standard cells are still overlapping with each other. So we need to find out what is the problem behind this red color hotspot. Okay, signal integrity. As I mentioned earlier, that is actually with the crosstalk noise. So when actually two nets run parallel for a long time, so it will actually create crosstalk noise. So it is advisable to break the distance between the two nets. So break the distance between two nets so that it is easy for the tool to skip crosstalk violation. So the affected net here is the victim and the switching net here is the aggressor. So how do we control crosstalk noise? Crosstalk noise actually can be controlled by limiting the length of parallel nets. So we need to avoid the length of parallel nets, and also we can also shield the special nets. So this actually prevents crosstalk. Okay, now routing is complete, and you're able to see that all the internal cells are being routed with each other. But still after routing, you're able to see few spaces. You are able to see a space here and two spaces here. So what happens is there is a cell called the filler cell, which is actually part of a standard cell library. These filler cells are actually dummy cells, same as the SPAT cells. So all these cells are used to fill up the gap between the standard cells to ensure that there is proper rail connectivity. For example, if there is a space here and there is a disconnect in the power rail connectivity. So when you put a filler cell in between, there is proper continuation of standard cell power rails. So here if you see that the filler cells are being connected, and now the routing is complete. The design is entirely done for physical design flow. Okay, the next step is static timing analysis. So static timing analysis is nothing but a technique used to verify the timing of a digital design. So what happens here is both setup and hold time is being checked, and many fixes are being done to meet timing. So as a physical design engineer, it is our main goal to meet the timing requirements given by the customer. So ST can only check for timing and not functionality of the circuit. So okay, so what is setup time? Setup time actually is the minimum amount of time the data signal should be held steady before the clock's active edge. So the data are sampled, whereas hold time is the minimum amount of time the data signal should be held steady after the clock active age. So now if you see here, you have clock path and data path, and the minimum amount of time the data signal is being held before the clock active age is setup time, and the amount of time the data is held after the clock or active age is the hold time. So this is the setup hold window, and previous to this and after that the data can toggle in this region. So this is actually a main concept. We need to remember that setup time is the amount of time the data signal can be held stable before the clock's active age, and the hold time is the amount of time the data signal can be held stable after the clock's active age. So this is a very important point. So required time is actually time required for data to arrival at a certain point. And arrival time is the time at which data arrives at a certain point. Okay, the difference between required time and arrival time is slack. Positive slack actually indicates that design is meeting timing, whereas negative slack indicates that design is not meeting timing. So setup slack is actually required time minus arrival time. Hold slack is actually arrival time minus required time. Positive slack is actually the required time is greater than the arrival time, and negative slack is actually the arrival time is greater than the required time. And we also have a definition which is clock latency. Clock latency is nothing but a combination of source latency and network latency. Source latency is from the external source to the clock source, this latency, and the network latency is from the clock source at the boundary of the chip to the internal register. So the delay through the register is calculated as network latency. So combination is the clock latency. Clock skew is actually difference in arrival time of the capture edge of two adjacent registers. So okay, so here if you see, it is actually there is positive skew. Here you have a launch clock, and here you have a capture clock, and here if you see, positive skew is where capture clock comes later than the launch clocks. Here in positive skew, the launch clock comes first, whereas in negative skew, the capture clock comes first. So the launch clock is late than the capture clock. Okay, so in static timing analysis, we need to make sure that we are aware of the details to be analyzed. So the details to be analyzed is we need to analyze the timing path. Timing path consists of start point, computational logic, and end point. So start point is actually start of a timing path where the data is originated as launched, and start point consists of a clock, primary input, etc. Computational logic, as we all know, is AND or XOR elements, and they actually contribute to timing violations based on their placement. Endpoint is actually end of the timing path. So we need to make sure that the timing is always checked between start point and end point with combinational logic in between. There are 4 timing paths to be checked. One is input port to register, which is the input to register, register to register, register to output, and input to output. So as a physical design engineer, we need to check timing across these 4 paths. So which is known as into reg, reg to reg, reg to out, register to out, and into out. So all this can be seen in your timing report. And also your log file after each step will have this kind of information. Okay, as we all know that there are two kinds of violations, timing violations we have in physical design, which is setup and hold time. So how do we fix setup violations? We can upsize the cell, we can insert buffers, we can reduce clock uncertainty, and we can increase the delay in the clock. And how do we fix hold violation? We can add delay, detour the routing. So if you have a long route, you can detour the route, so it will help you for in some margin to fix the hold violations. Okay, so this is actually a prime time timing report where you have a start point, you have an end point, and you have a path group. So the start point and end point should belong to the same path group, and the path type is max. Max is setup time, and path type min is hold time. Here you have data arrival time. Data arrival time is through all the flops, and data required time here is 10 nanosecond. So you have a data required time of 10 nanosecond, data arrival time of 739 picosecond. So since your required time is more than your arrival time, you have a positive slack of 9320 nanoseconds. All these are examples. And here you have path 1, which is met. Met means timing is already met, you don't have to fix. So it is setup time. And here your required time equal to arrival time, phase shift minus setup plus other end arrival time. And arrival time here is obtained to all the flops. Here your DFF, inverter, etc. So it is 0.827 is your arrival time. 10 nanosecond is your required time. So your slack is 9 nanosecond. 9 nanosecond positive slack. Okay, this is example for a whole timing report. Here your required time equals other end arrival time plus hold plus phase shift minus the cycle adjustment. All these are formulas, and your slack equals arrival time minus required time. Required time is 20 nanosecond and your arrival time is 0.117. So which means your slack equals minus 20 nanosecond. So it is failing by 20 nanosecond. Okay, so now we have come to the last topic for today's webinar, which is physical verification. Physical verification is very important in physical design because physical verification and static time analysis are the main checks to be cleared before the design is given to the foundry for manufacturing. What are the types of physical verification checks? Design rule check DRC, layout versus schematic LVS, electrical rule check ERC, XOR, which is to compare two databases, and logical equivalence check is the LEC. Design rule check. DRC is actually a process where the physical database, design database is checked against design rules. These design rules actually are provided to you from the foundry for each technology. Suppose if you are working for 40 nanometer, they have a specific set of guidelines for physical checks for 40 nanometer. And these design rules are provided by the manufacturers to the design engineers, and DRC should be cleaned before the design is given to the foundry. What are the types of DRCs? We have minimum width of a metal layer, shorts, minimum spacing, minimum width and spacing for VRs, etc. Okay, this is an example for a short. I hope that you are able to see that this is a different net name and this is a different net name, but they are of the same net type, so they short together. Here you have a spacing violation because of this VR. Here you see that you are able to see a spacing violation because the space here is quite big, whereas here it is quite small. So there is a spacing violation here. And what happens is, how do you fix this violation? You can extend this. This is metal 3 and this is metal 2. You can extend this metal 3 to this area and you can drop a VR, so that here you have metal 3 and metal 2 will not short together and will not have spacing violation. So this is how we can fix this violation. These are actually small examples, but in real projects we will have more complicated DRC violations. So it is best that DRC violations can be checked in each step of the design instead of doing it at the end. So in each step there are commands like verify DRC, verify connectivity to check the shorts, opens, everything. So it can be done parallelly in the design process. There is min area violation. So here if you see these two structures are of the same kind, whereas where you have metal 3, a via and metal 2, here you have metal 3, a via and no metal 2. So the problem is this via placement will require a certain metal 2 layer for a certain dimension. So you need to increase this metal 2 and this will actually resolve the issue. Okay, what are the basic DRC checks? There are 3 basic DRC checks, which is actually width, or the width of the metal layer, spacing of the metal layer, and then enclosure. So there are 3 basic DRC checks, which is width, spacing, and enclosure. Okay, next one is layout versus schematic check. So you are able to see here, which is the GDS layout, which is an output from our physical design flow, and this is an input to the physical design flow, which is the transistor. This is the layout of the transistor, and this is the schematic of a transistor. So you have an extracted netlist, you have a source netlist, and you compare these two netlists, and you have a LVS report. So LVS check is mainly to make sure that your layout and your schematic remains the same. So there are types of LVS errors: shorts and opens. Shorts and opens should always be fixed in your design. Unbound pins. So if the pins actually don't have a geometry in physical design, but they still remain in the netlist, we have to fix it. And there may be also VDD and ground opens in the design. So all this has to be fixed for complete proper connectivity. You can see here LVS is open, where you have open connection here, which is not connected. And LVS is short here, where you have a straight net and this is a different net, but they are the same net type and they short with each other. Electrical rule check, ERC, is a methodology used to check robustness of a design. So electrical rule check actually checks for floating gates, shorts between drain and source in a transistor, floating interconnects, etc. XR checks actually run where the original and modified database is compared. Okay, this actually is a very critical check. For example, if a customer, if Apple has released iPhone 10 and you have the database with you, you have the layout database with you. After 1 year, the customer comes up with a request that we have a few modifications done in the design. A few bugs have been fixed and it's a version 10.1. So in version 10.1, what happens is the front-end team will make the fix in the netlist and the back-end team will replace the spare cells with the new cells, and then the required modification given to the company is the customer gives a request that we only need metal 2 and metal 3 to be modified, because when they modify each layer is a cost to them. So they give you a request that only metal 2 and metal 3 modifications can be done only in metal 2 and metal 3. So what happens is the physical design engineer will then, based on the bug fixes, he will modify he will do the fixes with metal layers, and then at the end, before we give it to the foundry, a check is being done, which is known as XR check. What happens is the old iPhone 10 database is taken and the new iPhone 10.1 layout database is taken. So these two layout databases are compared, and there is a report generated. So this report generated should only have changes in metal 2 and metal 3. So if there are changes only in metal 2 and metal 3, we are good to go, and we can inform the customer that we have done only changes in metal 2 and metal 3. But when you do an XOR check, if you come across a change in metal 2, metal 3, and metal 4, then you need to fix this issue, because the customer has given you a request that only the fixes can be in metal 2 and metal 3. So we need to make sure that only metal 2 and metal 3 is being modified. So we need to again modify the design, modify the layout, metal layers, and make sure and check why metal 2 is shown as change, metal 4. So this is why we do the XOR check. Logical equivalence check. This actually is nothing but to check if the design is logically equivalent, even though after it has gone through lots of optimization stages. So here first you have an RTL, and the RTL is a modified RTL, and you check whether it is logically equivalent. And then this RTL, modified RTL, is actually converted to a gate level netlist, and you again check whether it is logically equivalent. And this gate level netlist is given as an input to the physical design team, and the physical design team does clock tree synthesis, they add repeaters, they do placement, routing, and optimization is done, and still we check whether it is logically equivalent. So the ultimate aim behind this check is to make sure that even though the design has gone through lots of optimization steps, the function still remains the same. So your front-end function of the front-end team and function from the back-end team is still the same, even though circuit is being replaced with metal layers. So this is the logical equivalence check. So with this, we come to an end of today's presentation. I have a few more slides, which is just to give you an awareness of life in VLSI, the courses, job scope, and companies. Okay, there are some online certification courses. They are in India and also in US. So this will actually give an insight, in-depth study and certification with hands-on for VLSI and certain topics, particularly in VLSI, physical design and front-end design. Okay, so VLSI studies internships in India. We have IITs, NITs, BITS, Bilani, top universities in India, and VLSI research labs in IITs, and also few universities which focus mainly in VLSI have research labs, and you can write to the professors, and the professors will be able to guide for internships, for research postgraduate projects, research fellowships, etc. And VLSI studies and internships in abroad. We have NTU in Singapore, which is Nanyang Technological University, the National University of Singapore, German Institute of Science and Technology in Singapore, which offers the NTU and TEM joint degree program in IC design, University of California, Berkeley, and MIT, Stanford University, Georgia Institute of Technology, University of California, San Diego, and University of Michigan, University of Texas, University of Southern California. Okay, so job roles in the semiconductor industry. We have design engineer roles, verification engineer roles, application engineer roles, manufacturing engineer roles. So design engineer roles include front-end design, which is they deal with VHDL verilog coding, back-end design, which is physical design. We have FPGA, which is field programmable gate array engineers, DFT design for testability engineers, analog mixed signal engineers, RF engineers, and IP design engineers. And we also have verification engineer roles like front-end verification. Once the front-end team designs the circuits, the netlist, the verification is being done. And we have EDA tool validation like Cadence, Synopsys, Mentor Graphics are EDA companies. So when their tools are being purchased by a company, the company will have an EDA validation engineer. So he will run the tool to make sure that it works properly and it is meeting their requirement. And then after that, it is given to the pool of engineers to work on. So we have IP verification engineers. So application engineers include corporate application and field application engineers. So corporate application engineers are engineers who come up with presentations to companies to market their products, their tools, etc. And field application engineers are engineers which go and they fix the bugs, they debug issues in the tools during projects in certain companies. Manufacturing engineers are actually foundry fab engineers, fab managers, technical support technicians, and also the clean room engineers who wear the white dress and they work in the clean room to manufacture the chip. Okay, the major recruiters in VLSI are ST Microelectronics, which is a French company, MediaTek, which is a Chinese company, Infineon is a German company, TSMC is a Taiwan company, NVIDIA is more into graphics. It's a US company. Qualcomm is more into 5G communications. Intel, as we all know, is everywhere. And Xilinx is into FPGA, which is a US company. NXP is a Europe company. Micron is a US company. Broadcom is a US company. Texas Instruments is a very old US company. Cypress Semiconductors, Broadcom Limited, and so on. So, and the last three companies we have, Cadence, Mentographic, Synopsys, are EDA tool companies. So all these tools are being used by the above companies. So all these companies have their design centers in India, in Chennai, Bangalore, Noida, etc. And they have their strong presence in Asia. So with this, we come to an end of today's webinar on physical design and its role in the semiconductor industry. So feel free to write to me if you have any queries regarding physical design, and you can also contact me through LinkedIn. And once again, I thank the institution for giving me this opportunity and to be a part of this AICTE knowledge sharing program.
Dear participants, any queries, you can unmute yourself to ask our resource person.
Dear participants, is there any queries? Feel free to unmute yourself and ask with your resource person, or you may put your questions in the chat box too. Sir, I think there is no more questions. Hello, sir.
Okay, sir. Okay, sir.
Shall we end up the session, sir?
Okay, yes, sir.
Nothing new can come into your life unless you are grateful for what you already have. In this way, I would like to thank our resource person, Mr. Samuel Jigme Harrison, ST Microelectronics, Asia Pacific Private Limited, Singapore, for enrich our knowledge with his ideas. Thank you, sir.
Yes, thank you, sir, and thank you everyone for sparing your time today for this session, and I think this session was useful for each one of you. Thanks.
Thank you.
once again.
Dear participants, the day 8 session to attendance and feedback link is posted in the chat box. While filling the feedback form, please select your respective FDP ID. Thank you.
So thank you, sir. Thank you very much, sir.
Yeah, thank you, sir.